Hello, Math Study students, and welcome to your online lesson. Today we'll be starting a new unit on sequences, and so our goal is to define sequences and related terms, and also define arithmetic sequences and any concepts related to those arithmetic sequences. We will know we are successful when we can identify sequences and find unknown values from arithmetic sequences. So our first question is, what is a sequence? Well, a sequence is a list of numbers where there's a pattern. So I could take a random number like 2 and then go to 5 and then 8 and then 11. And it might just look like I'm just sort of listing off some numbers that are increasing in value, but there's a specific pattern here. You will notice that to change a 2 into a 5, I'm actually adding 3 on. And then to change that 5 into that 8, I'm following the same pattern where I'm adding 3 more and then add 3 more to change it into an 11. 3 more will change it into a 14 if I wanted to continue, and then 17 and 20 and so on and so forth. The pattern can continue on indefinitely. The members or the numbers of that sequence are said to be terms. So the first term of the sequence that really didn't have anything to do with the pattern, was just a random number, is the 2. That is our first term. And then we have our second term being 5. So even though it's the second term, it doesn't mean its value is 2. The first term actually had a value of 2, but the second term had a value of 5. Our fourth term has a value of 11. Our sixth term had a value of 17. Terms. Again, it's those terms that are the values that are members or part of the list of numbers that we have here in our sequence. And again, it's just a list, a running total. So here we have some lists that have been started for us. We want to describe the sequence and then write down the next 2 terms. So our first term here is 78, and then we go to a 71, 64, 57. We can clearly see that our values are getting less. So I kind of want to figure out what's going on in between these. And if I take 71 and subtract what I started with, 78, I end up with a -7. So it looks like I'm going down 7. And then I can check to see if that holds true for the next one. And so if I subtract 7 from 71, I do end up at 64. And if I subtract 7 from 64 or add a -7, I end up at 57. So what's going to happen next? Well, if I take 57 and subtract 7, I end up at 50. And if I subtract 7 from 50, I end up at 43. So those would be the next 2 terms, the 5th term and the 6th term, because 4 terms were already given. Now, as I look at this next one, I've got the 3 going to the 6. So that's getting bigger this time. It's getting bigger by 3. And then as I go from the 6 to the 12, I'm getting bigger by 6. And then from the 12 to 24, I'm getting bigger by 12. So every time I got bigger by the same value that I just had written down. So essentially what's happening is I'm doubling. I'm taking 3 times 2, and then that gives me 6. And then 6 times 2 gets me 12. And 12 times 2 gets me 24. And 24 times 2 gets me 48. And 48 times 2 gets me 96. So those would be our next 2 terms. All right, looking at our last list of numbers that we have here on this example, as I look at the difference between these, I've got a 1 to a 3, which is a difference of 2, and then I have a difference of 3. 3 more will get me up to 6, and then it's a difference of 4. So it looks like I'm growing by an increasing amount each time. So the first time I was growing by 2, and then growing by 3, and then growing by 4. So the next one I'd want to grow by 5, which would get me up to 15. And then if I want to go to the next one, I would grow by 1 larger, which is a 6, so I'd be up to 21. And those would be our next terms. So that's sort of a weird one where the pattern is consistent because we're always adding 1 additional value on, but the change within the terms is constantly increasing. All right, so those are just some random patterns that we had there. Now what we're going to look at are sequences that follow a very specific sort of set of rules, I guess is the best way to say that. So a couple things to keep in mind. A number sequence can be defined in one of the following ways. You could give a description in words. So start with a certain value and then each new term add on a certain value or multiply to get there, or again, just some sort of description explaining what that pattern is. Another way a number sequence can be defined is by listing the first few terms and assuming that the pattern represented continues indefinitely. And that's what we saw in the last example, where they were listing a few numbers, the pattern was shown, there were enough terms there that we didn't have to guess what the pattern was, and then we assume that it continues on that way. And then the last way, and this is pretty useful, is to write a formula that represents what we call the general term or the nth term. And those terms, if you will, that vocabulary is going to come back. So we need to know that. A formula is known as the general term or the nth term because it lets us know any value simply by plugging in a value. So it lets us know any term value essentially by plugging in a value of what we're looking for, like the 10th term or the 100th term or the first term, something along those lines. So we'll take a look at a couple examples of these moving forward. Before that, I mentioned that we were going to talk about some specific types of sequences, and one specific type of sequence is known as a geometric sequence. So we have taken a class called geometry, which involves shapes and things like that. This is a little different than that. This is a pattern where the same number is multiplied, or essentially divided, where you'd be multiplying by a fraction, to get to the next term. And we saw an example of that where we were multiplying by 2 a couple slides back, and we kept multiplying by 2 every single time. So we kept using the same value to multiply. And then an arithmetic sequence, which is actually one of the goals of our lesson here, is a pattern where the same fixed number is being added or theoretically subtract if you're adding a negative to get to the next term. And we looked at a couple examples of that. The first example I gave with the 2, 5, 8 sort of thing, we were adding on that same value of 3 every single time. And then we saw another one later on where we were subtracting 7 every time. And both of those would be arithmetic sequences because we're adding or adding a negative, essentially subtracting that same value over and over again to follow that pattern. So I had mentioned formulas, and for an arithmetic sequence with a first term u sub 1 and a common difference d, the general term is as follows. So we are essentially taking our first term, whatever our first number was, however much we're increasing by, that constant value that we're adding on over and over again, and the number that we're actually looking for, aka the first term, the 50th term, whatever, to find our term of that value. So let me look at an actual example of this. So let's say we go back to that first example where I had a 2, a 5, an 8, an 11, so on and so forth. And so I would need to fill in my u sub 1. Let me write this whole thing down again. So u sub n, u sub 1 plus n minus 1 times our common difference. So u sub n, this is right here our first term. Well, what's our first term in this case? It is 2, because that was the first number we had listed in our pattern. Now, what is the common difference? Well, common difference is where you subtract any two values, and you always subtract backwards. So I take my 5, for example, and I subtract the term that came before, which was 2. So my common difference is 3. Now, I should be able to do that for any of these values if it's truly arithmetic. So what if I did the next two? 8 minus 5. Well, again, I get 3. What if I did the next two? 11 minus 8. And again, the common difference is 3. So when I have a common difference, that is going in place of D right there. And our case would be 3. Now the n minus 1, I want to leave that, because that is going to allow me to plug in any value for n to find my term number. And u sub n is just a representation of that term. So let me give an example of that. We already know that the fourth term in this pattern is 11. So if I wanted, but let's pretend I didn't know that. So let's say I was looking for the fourth term. So I'm writing that as u sub 4, which just means the fourth term. So it's not the number 4, it's just the fourth term in the pattern, whatever that is. And so then I have my first term here, plus n, which was 4, because I'm looking for my fourth term, that's my term number, minus 1 times 3. Well, what is 4 minus 1? That gives us 3. So we're going to have 3 times 3, times 3, plus the 2 here, equaling my fourth term. And then if we simplify this, we have 3 times 3, which is 9, plus our 2, which gives us 11, so that we know our fourth term is 11. So that's an example of using the general term. Now, which step along these lines were the actual general term? This is just a formula right here. But this one, once we plugged in our first term and our common difference, that became our general term. And we call it the general term again because I can use it to find any other term. All I have to do is plug in a value for n. And you'll notice this n here and this n here, I plugged in the exact same thing, which was 4, to find the value of my fourth term. Going back to this formula, which is our common difference. Common difference, we take our term of 1 higher and subtract the term that we're talking about. So I could subtract let's say this was my third term, then I would be subtracting it from 1 more than the third term, which is the fourth term. Or if n was originally 2, then 1 more than that would be 3. So I'd be taking my third term minus my second term. And again, that just means third term minus second term. We're subtracting backwards. We're working backwards to find that common difference. Okay, we're going to do one last example in this video. So we're given the exact same pattern that we were just looking at by coincidence here. And we first want to show that the sequence is arithmetic. So in order to show that it's arithmetic, you have to show that there's a common difference. And I want to be really clear on this. For any test that I give or any IB exam, in order to show that it is arithmetic, it has to have a common difference. And difference means subtract. So you would take the first two terms and subtract backwards, 5 minus 2. And that should be equal to 3, which is the same thing as if we take the next two terms, 8 minus 5, also equal to 3. And then we would take the next two terms, but subtract backwards, 11 minus 8, all equaling 3. So we have a common difference, or D, of 3. And there's no other acceptable way to show. So you can't say, oh, we're just adding 3 every time. Look, no, you have to show me by subtracting backwards that there's a common difference of 3. Now we want to find that formula. So the same thing that we did on the previous slide, I'm simply going to write it down. We have u sub n is equal to u sub 1 plus n minus 1 times d. So this isn't quite our general term yet until we plug in our values for u sub 1 and for d. Well, we already know those values. So u sub n is equal to our first term, which is 2 plus n minus 1 times our common difference, which is this number right here, 3. You could also sort of expand this. You could multiply the 3 to the n and the negative 1, and that would be fine as well. And let me show you what that looks like. You don't necessarily have to do this, but you could. And so we'd have u sub n now is equal to 2 plus 3n minus 3. And now we could combine like terms, which would be our 2 and our negative 3, giving us u sub n is equal to 3n minus 1. And that might be a slightly easier way to do it once you've sort of simplified it. And now it's even easier to plug values in, which gets us to our part 3. Now we want to find the 50th term in the sequence. So we are going to let n be 50. So we have u sub 50. Again, we're replacing this n right here with the 50. And now that represents our 50th term. U sub 50 is our 50th term. And to find its value, we're simply replacing n again with 50. So this n right here just got replaced with a 50 minus 1. And so u sub 50, or the 50th term, is equal to 3 times 50, which is 150, minus 1, which is 149. So this is great notation. It's sort of a function notation because it lets me know that, hey, this was the 50th term in the pattern, and that 50th term is 149. Now the next question is 376 a term in this sequence? So I'm going to clean things up a little bit here. We'll get rid of that last part. So if it's a term in the sequence, then it can replace a u sub n. And if it's a term in the sequence, it will have a term number, like the first term or the 5th term or the 20th term or the 100th term. There is no 1.5 term, so I have to get a whole number for my term value. So I'm going to take 376 I'm going to replace the u sub n with that. So I'm pretending that it's a term value. And then I'm going to just write 3n minus 1. To get n alone, I'm going to add 1 to both sides. I get 3n is now equal to 377. And when I divide both sides by 3, the question is, do I get a whole number? And when I take 377, and I'm using a calculator right here to divide it by 3, I end up with 125.7 approximately. And that's not an actual term value because it has this decimal. It was 0.6 repeating, really. So this is not a member of this sequence. We're going by threes, but we skip right past that number, 376. Let's try it one more time. Now we're going to try it for the value of 404. So I'm plugging in 404 as a possible term value, setting it equal to 3n minus 1. I add 1 to both sides. I get 3n now is equal to 405. Divide both sides by 3. And this time, when I use my calculator, 405 divided by 3 gives me a whole number answer where n is equal to 135. So in this case, is 404 a term in the sequence? The answer is yes. And not only is it a term in the sequence, we know that it is the 135th term in that sequence. All right, so that is going to do it for today's video. More on this next time.